Hi, in this video I'm going to talk about this type of diagram. Diagrams like this play a very important role in signal processing. Engineers like to use diagrams like this to describe systems. You can see that this is a diagram of a continuous signal processing system because it has the A instead of the delay D. A is an integration block. But really, the way you analyze these diagrams is the same whether or not the system is a discrete signal processing system or a continuous signal processing system. The idea is you want to change this diagram into an algebraic expression that relates x and y. In other words, get the transfer function. And I personally have found this quite confusing. There's so many arrows. How do you get equations from the arrows? So I've thought about this quite a bit, and here's a strategy that I found seems to work very well. Okay. First, label all the nodes with branches. Now, what do I mean by this? Here's a node with a branch here and doesn't have a label. This y is actually labeling this node here. It's labeling the arrow, but the arrow is the same as the node. This y also is labeling this node. This doesn't have a label. So label all the nodes with branches. Okay. Now, number two. Label output arrows from system components based on immediate inputs. Now, what do I mean by a system component? Well, this is a system component. It's a multiplier. Multiply by minus 0.9. What's an output arrow from this system component? Well, that's the arrow out this way. Okay. You can see that each system component has one output arrow. Right? So that's unambiguous. Now, according to this rule, if I label output arrows from system components based on immediate inputs, I would label this output arrow here based on immediate inputs. What's the immediate input? The immediate input is from here, it's from y. Okay? So the output arrow here I would label as minus 0.9 y. Now I'll do an example and write it out. I'm just trying to go over the rules and explain what they mean. So in this case, it's clear. What about this output arrow? Well, I say label output arrows based on immediate inputs. Okay. So the immediate inputs here would be this arrow, this input arrow, and this input arrow. Now this is going in, but this is a secondary input, right? So it's going from here to here to here, but I want the immediate inputs. Okay. So we'll do that. Now, if I wanted to label this arrow, right away I couldn't because I don't have a label for this one. But so what you do is you label arrows as you go, and you can fill in as many labels as you need. Okay. Okay. Number three, equate nodes with arrows going into them. Eventually, I will label this the output arrow from A. But I'll also have, by that time, I'll have a label for this node. Then I equate those two expressions, and that will give me an equation. Okay. And then use these equations to solve for the variables you want. So when I get the unknowns, I'm going to get more than one equation, but I can eliminate the variables I don't need. Okay. So let's go ahead and do both of these examples using this method and see how if that's helpful for you. Okay, so I've copied this diagram, and let me make it a little bit bigger so that it's easier to label. And I'll use red for the label. All right. So the first was label all nodes. Oh, I think I need to make the pen a little smaller. That should be fine. All right. All right. So label all nodes with branches. That was the first item there. See at the top there. Label all nodes with branches. So the nodes that have branches, well, there's this one here, and I'll call this W. Now, as I said, this Y can be thought of as this node also, so I'll label this as Y. It's the same, it's really in the same place. It's just written over here. All right? Part two was label all output arrows from system components based on immediate inputs. So let's start from the left to right and see what we can do about this. All right, so here's a system component here, the minus 0.7, and I want to label the output of that. Well, the immediate input is just from the W, right? So this is just going to be minus 0.7 W. Okay. Right. Now having this arrow, I can now label this arrow here, right? Because I know the two immediate inputs. Okay. Okay. So that arrow there is going to be, well, the first immediate input was X, and second immediate input was minus 0.7 W. So that's X minus 0.7 W. Okay? All right. Next, I now can find the output arrow for A. All right. Now, you might wonder, why is he doing it in this order? Well, you can do it in any order. All right. It doesn't really matter. I'm doing this because I want to get right away as soon as I can to an equation for W. But if I label A based on the output of A, based on the immediate input of A, well, the immediate input was this X minus 0.7 W that I just came up with. So this is just going to be, this, I can label this here, X, so I can label it A times X minus 0.7 W. Now, it may seem a little confusing that you're using A here, which is a component, and X, which is a signal, and you're treating them as if they're the same thing. But you actually do something similar in linear algebra when you have matrices and vectors. In fact, there's a close connection between A and matrices and X and W as vectors. Right? So I've labeled this output arrow. Now, this output arrow is the same as W. All right? So that gives me an equation, all right? By equating these two here, that gives me W equals A times X minus 0.7 W. Okay? All right, now let's do the same with the others. I'll use a different color. Just to distinguish, we'll use the magenta. All right, now this one you can see is almost exactly the same thing. Here's a y, so this one is going to be minus 0.9 y, and then you put that in here. So now this one here becomes W, which is the immediate input. Now you might wonder, well, should I write W or should I write this? It doesn't really matter, because those two are equal. I have that equation already. Okay, so this is going to be W minus 0.9y. Okay, hope you can read that. Okay, all right, and this is A times W 0.9y. A times W minus 0.9y. Okay. Okay. All right. And that output arrow there is equal to y. Okay, so these two are equal, and that gives me another equation. So let me circle that in purple, and I'll have my purple equation here. It's a little bit thick, right? So my purple equation is, let me thin it out before I write something. Is it going to go for me? There we go. Okay. Purple equation is going to be y equals A times W minus 0.9y. Okay. All right, so now I have my two equations. Then I'll use these equations to solve for the variables I want. So I want to eliminate W. Okay, so let's do that. We can actually we can solve this one for, like, we can solve the first one for W, and we can solve the second one for Y. And when we do that, we'll see something that we've talked about before. So if I solve the first one for W, I'll take W plus 0. Bring the W's to the other side, equals AX. And that gives me W equals A. Now these operations commute, so I don't really have to worry about how I write this. X. Okay. And then here I have the purple equation, gives me this very similar equation for Y in terms of W. It's going to be Y, and then it's going to be plus 0.9 AY equals AW. So Y equals A times 1 minus. Did I say 1 minus? It should be 1 plus, right? So I'll fix that. 1 plus 0.9 AW. All right, so let me fix that with the right color. Okay, and it should be a plus. Okay, all right. Now, so now we can eliminate W. If we eliminate W, then we get Y equals A over 1 plus 0.9A times A over 1 plus 0.7A times X. And we get the same result that we saw before, is that the transfer function for two systems in series is just the product of the transfer functions. Okay, so I can write that here. The transfer function for a system consisting of well, I could say two or more, right, subsystems in series is equal to the product of the transfer functions. Okay, all right, very nice that you can change this everything into algebra. All right, good. So let's go over and do the second one, which is a little bit more involved, and this is the one that really caused me trouble. Okay, so let's use a similar strategy. And I'll start out with my red again, just like I did before. All right, so first I want to label the nodes with branches. And I got one here, that's my W. And then I've got one here, which is my Y. Okay, that's step one. Step two is label the outputs of system components based on immediate inputs. So I'll start again with this one here. This one here is going to be K1W. Okay. What about this one? Well, this is K2Y. Okay. Now, what about this one? This one is, what about this one here? That one there is going to be X plus K1W plus K2Y. Okay, not too bad. Okay, and then this one here is now going to be A times X plus K1W plus K2Y. Okay? All right, so I've got my first equation here. A times X plus times, well, let me get up here so I don't want to talk ahead of myself. Right? So this one here is going to be, I'll circle it. I equate these two. So that gives me W equals A times X plus K1W plus K2Y. Okay? Now let's go ahead and do the other, well, let's see, what other branches do we have? It's just this one here. All right, now, you can see here that the output branch here, I want to do a different color now because I do want to distinguish. Let's do the cyan. I want to do this one here. Now, based on the immediate inputs, that's just A times this. So it's just A times W, all right? So you also have Y equals A times W. Okay? All right. So we can do the same thing. We can go ahead and solve for W and then plug in and eliminate the W. So we want to eliminate W. Now, you might say, well, let's apply A inverse and say A inverse Y equals W. Now, you could probably get away with that, but you don't want A inverse in your final answer. So you just don't use inverses and solve it directly. Well, actually, when you're taking 1 over, that's like an inverse. Let's just solve it directly instead. So I think that will get us there quicker. So if we solve this first equation for W, put W on one side, I'm going to get W minus K1 AW equals A X plus K2Y. Okay, or that means that W equals, I could factor out the 1 minus K1, so that's going to be A over 1 minus K1. Now again, I don't have to worry about commutative. I can use all my ordinary algebraic properties to do this. Minus K2Y. All right. Okay. Now, to find Y, I just multiply both sides by A. All right. Piece of cake. So Y equals AW. That's equal to A squared over 1 minus K1A times X minus K2Y. Okay. All right. Now, I don't need to substitute for Y over here because I've eliminated my W, and I can go ahead and solve for Y. Okay. So what does Y give me? Y gives me, well, I want to bring the Y to the other side, so I'm going to have Y. Now the Y term over here is going to give me a plus K2 A squared over K2 A squared Y over 1 minus K1A. Okay. And then here I'm going to have equals A squared over 1 minus K1A X. Okay. So I certainly want to combine this all together. If I put this over a common denominator, I'm going to get Y. So I'll get 1 minus K1A plus K2A squared Y over 1 minus K1A equals A squared over 1 minus K1A X. All right. And then I don't need to worry about dividing by 0 here. There's a reason for that. The integrator block is never going to be equal to the identity. So I don't need to worry about dividing by 0. So I can just say 1 minus K1A plus K2A squared equals A squared X. And that, sorry, I forgot the Y. And then just divide. So I get Y equals A squared over 1 minus K1A plus K2A squared X. Okay, now the problem was asking how can you make the two circuits equivalent? How do I choose K1 and K2? So if we compare this expression here that we just have with the expression that we have up here, You can see we still have the a squared on the top, but the denominator here is 1 plus 0.9a times 1 plus 0.7a. So in order to make them be equivalent, right? So to make these two systems equivalent, we must equate the denominators. Okay, so that's going to give me 1 plus, whoops, sorry. Okay. All right, we have a little glitch here. 1 plus 0.9a times 1 plus 0.7a equals 1 minus k1a plus k2a squared. And if you work that out, of course, this becomes 1 plus, then 0.9 plus 0.7 is 1.6a plus 0.63 a squared is equal to 1 minus k1a plus k2a squared, and that gives you k1 and k2. Now, if I made an algebra mistake, you'll be able to trace it back, but that's the process. So I think that works pretty nicely, and hope that's helpful for you.